Okay, thanks. You get the first slide up. So I'm filling in for Kevin McPherson, who is away, but he's the manager of the Microgravity Acceleration Measurement Program at Glenn. And so, can I pull this out? Okay. So let's see. So it's based at NASA Glenn Research Center. If you have any detailed questions, you can always ask Ken All, because that's where he used to work prior to his working with ISS. So he can correct me as we go. I'm speaking here as a user of acceleration services. As you hear later, my area is really microgravity combustion. The next slide, please. The program at Glenn, the principal investigator of microgravity services, has been in place really since the shuttle era, and we support the International Space Station acceleration measurement systems, and we process, analyze, and accelerometer data to characterize the microgravity environment of the ISS for the PIs and for the ISS community. And we've got a long history of microgravity environment support, both on the shuttle, Mir, and in the ground-based facilities, including aircraft. And we assist the PI team in understanding the different aspects of measuring and interpreting the microgravity environment, and that plays both into interpretation of your experiment, but also in design of your experiment, and provide interpretation of the environment and perform detailed analyses for general and specialized characterization. And it's a sort of a one-stop shop for ISS acceleration data, regardless of whichever measurement system is in place. And as you'll see, there's several different systems in place because acceleration measurements go over a wide range of conditions and locations. Next slide, please. This is a simplified diagram of the components of the microgravity environment, and because really, depending on what you're doing, you care about the acceleration over range from the truly steady state all the way up to hundreds of hertz, and also there's transient. So basically, when we speak of the quasi-steady conditions, we're talking about less than 1/100th of a hertz, and typically for the space station, you're talking about micro-Gs or less at peak levels. And this is a result of the gravity gradient, rotational effects, where you are compared to the center of mass in the vehicle, and function of attitude, and whether venting, vehicle's venting. Certain classes of experiments care deeply about this, particularly the sort of materials and ones like that. My area of combustion, this really is not a big problem for us. We get care more in the vibratory area, and this is ranges from 1/100th of a G, 100th of a hertz, up to roughly 300 hertz is where our measurements, and it can vary up to in the milli-G range, depending on the frequency range. And this is from all host of equipment. Pumps, fans, compressors, the crew, exercise, and the structural modes of the vehicle itself. And then, of course, you have the transient effects, which can be, very large, because this is when the actual things like docking occur, and the crew near your rack can also induce a large force if they're moving things around. And so, depending on your experiment or what you're trying to do, you really have to pay attention to all these areas. And you're always going to have some transients, and you've got to be able to bridge across them if it's a problem. If you've got a short experiment, you can find a brief time when things are good. Next slide, please. And I guess okay. So there's a number of systems on the ISS, and the first one is the Space Acceleration Measurement Systems number 2, and this is a successor of the systems we used to have on the shuttle. And this is in the higher frequency range from 1/100th of a hertz up to 300 hertz. And right now there's 4 sensors within the U.S. lab at various locations, one each in the combustion integrated rack and the FIR, and 2 in the express rack. There are a couple within the Japanese module and 2 in the Columbus module. And all of these provide real-time downlink from the ISS. Next slide, please. The other system is called MAMS, and this is also NASA-sponsored. And this measures the more quasi-steady conditions and uses 2 types of sensors. The ORE sensor subsystem, which is, again, shuttle heritage system, and the MAMS HIRAP system. And the OARE is for the very low-level, low-frequency gravity levels, and the MAMS HIRAP sort of bridges between that and the SAMS data, going up to about 100 hertz, providing vibratory levels. And again, they provide real-time data downlink from the ISS. Next slide, please. And finally, the JAXA-sponsored MMA, or Microgravity Measurement Apparatus system, also measures the quasi-steady levels and the vibratory transient environment. And this was launched in 2008, and they've got 3 sensors within the Kibo module, but the data is not downlink real time, but you can get it after your experiment. Next slide, please. This just shows maps of locations of where the different kinds are. The MMA ones are in the Japanese module. We've got SAMS sensors here, MAMS, et cetera. And you can refer to this later if you want to try to, and they can work to help predict what, if you don't have one in your particular location, they can work to help predict what it would be like based on the sensors in another location. Next slide, please. So the cool thing is all this data is archived and is readily available, and so you can go through this PIMS website, and they've got all the data in very raw form that you can do your own analysis, but they also, and so they've provided, the advantage of this is it provides a standard data format for the ISS acceleration data from any of the systems, either from NASA, JAXA, or ESA, and provides access to the PIs. And basically, you've got pairs of files, one with the raw data and one with the other information about sampling rate, cutoff, where the measurement's made, and what the orientation of the vehicles, et cetera, and puts it all in a unified coordinate system. Next slide, please. Now, a lot of people are not going to want to do that kind of detailed analysis themselves and really want to just understand what they can expect. And through the PIMS handbook provides summarized acceleration information about the various disturbers in a common format. And again, this is available on the website. And typically, they have what they call a qualify page and a quantify page, and we'll see that in a minute. And that helps you sort of understand qualitatively, what's going on, and also quantitatively. And with the addition of the additional laboratories, provides additional characterization opportunities, because not only do you have more experiment sites, but now you've got more pumps and blowers and structural modes in the vehicle. So they really, there's a lot more things to look at. And so they've been working to characterize the known disturbance signatures in both laboratories. And because they've added, in addition to all the mechanics, there's also new crew exercise equipment as well. Next slide, please. So we got some examples, and we'll look at what crew exercise looks like, and both from what's the sort of resistive device and the an ergometer, one of the choices of ergometers, and then what docking and reboost activities look like, and what one particular facility looks like. Next slide, please. So this is a standard spectrogram, and this axis here is time, and so this is about half an hour across here, and this is frequency ranging from 0 here to 40 hertz, and the color is the power of the intensity of the acceleration. And so you can see, and this is done with a SAMS-2 sensor in the U.S. lab. Now, this is when crew members on this resistive exercise device, which is this static, it's not static, like weightlifting type resistance device. So they can do all kinds of different exercises ranging from squats, shrugs, deadlifts, et cetera. And so, and actually, if you look on their, it's hard for you to read here, but right now he's doing, or he or she is doing squats and heel raises, and you can see there's distinct intervals of those exercises. Then they go to deep, I can't read, there's here the one-leg squats and deadlifts and shrugs and bench press. So they've got a whole range of things going along. And so you can see that depending on where your experiment is, you need to expect to see accelerations of this level. Next slide, please. And this is what they call the quantify page, where it's RMS acceleration in milli-G during the same time period for the same location. And again, here, these are the different exercises marked. These are the squats and heel raises, et cetera. And this was actually, I forgot to mention, this was a quick exit out of the module. So he or she shot out of there, and that was a big disturbance. Actually, if you could go back one slide, I forgot to point that out. See, is that mark right there? So it shows up across a wide range of frequencies, but that was just the crew member leaving. Okay, next slide, please. And so you can see again, this is the net result. So this is getting up to a milli-G at the higher frequency levels. Next slide, please. So then this is an ergometer device, and this was the MMA system in the Japanese module. And you can see there's different, this is a aerobic type device. And so you can see, again, this is time, the scale is different. This is, actually this is an hour and a half across here, and going up to 25 hertz. And there's distinct modes, as you'd sort of expect from a ergonometric device. So most of it's at this, roughly 13 hertz frequency with other modes below. But there's cyclic effects as well. Next slide, please. And this is the cumulative RMSG over frequency. So you can then see that there's a whole bunch happening right there, and then pick up a bunch at 6 and 7 hertz. This is within for one particular time within that other graph. Next slide, please. And these are all examples of how types of analysis you can get, and which one you want to get really depends on your experiment. And what I really recommend is if you're or a payload. If you're thinking about doing a payload, go back and look at the other literature and where people have worried about the acceleration, and that's probably the areas you want to be most interested in. And again, it varies significantly between whether you're dealing with gases, high temperature situations like flame or fluids or whatever, or you've got an interface you're trying to stabilize. You really need to look at the particular G concerns for that experiment. And this is now a quantify graph for the docking of the first ATV. And this is the main impact, and then actually this is where apparently the docking latches are being clipped in, and it really is not noticeable against the background particularly, whereas apparently in the shuttle dockings they're much more noticeable. So, and this is the another typical example. Next slide, please. Could you go back, please? Oops. No, go back. Yes, this is the vector magnitude, but this is during a docking period. But so you're going to, big things happen when, and then as we'll see, there's a boost next where they're going to actually boost the station up. Next slide, please. And this is actually the reboost. So the ATV is now lifting the station up, and so you have a big. So it's a third of a milli-G, but it's on for 15 minutes, and so that's a substantial impact for almost anybody, and so you would not want to be operating a sensitive experiment during that time period. Next slide, please. And then this is looking at a particular facility, and this is now using the high-RAP sensor, and in the U.S. lab. And this shows, again, this is over, a number of hours, and 8 hours. And this is up to 100 hertz frequency levels. And you see there's big, strong impact from the blowers and then the pump and the fans, very steady over time. And I can't tell you, unfortunately, how close this sensor was to the device, but I imagine it's right in the same rack. But but it matters if you're building a facility. You've got to really pay attention to what you do to yourself and what kind of fans and blowers you put in your hardware. Next slide, please. And this is a power spectrum of the same thing. And the red is when the equipment is on, and the green is when it's off. This is a function of frequency at a time in there. And as you see that there's those modes where you saw the big pumps coming on, there's big changes in this. Impact. Next slide, please. So in summary, PIMS processes and data and stores acceleration data for the NASA's SAMS-2 and MAMS acceleration measurement systems, and we store the data for the JAXA's MMA system. And they've got archives available for each system in support of microgravity research and vehicle. And it's simple web-based access and standard formats of data storage. And there's a whole bunch of handbook pages which give you summary information of what a lot of disturbers look like. So you can use that to anticipate what you're going to see with your particular experiment. And